So we're going to look at graphing rational functions. And of course we know from Math 110, college algebra, that a rational function is a function that has a polynomial in its numerator and a polynomial in the denominator. And so one of the characteristics of rational functions is that they often have vertical asymptotes. So we'll say the line x equals a is a vertical asymptote of f of x equals p of x over q of x if, when f of x is simplified, x equals a causes the denominator to equal 0. Okay, don't forget, we don't just set the denominator equal to 0, but first we simplify the entire rational function, and then we set it equal to 0. The graph of a rational function never crosses a vertical asymptote. Now, our rational function may also have a horizontal asymptote. It says the line y equals b is a horizontal asymptote if either or both of the following limit statements is true. The limit as x approaches minus infinity of f of x equals b, or the limit as x approaches infinity of f of x equals b. That is, as x gets larger and larger and larger, or as x gets smaller and smaller and smaller, more negative, the function itself tends to balance out at a particular value. So it is possible for us to cross a horizontal asymptote, but eventually it tapers off and it guides our function. The horizontal asymptote will guide the function. So we're going to look at the three ways that we can determine what the horizontal asymptotes are. The first way, well, with all the ways, we look at the degrees of the numerator and denominator. If the degree of the numerator is the same as the degree of the denominator, the line y equals a over b is the horizontal asymptote. And a is going to be the leading coefficient of the numerator and b is the leading coefficient of the denominator. So when the degrees are the same, the horizontal asymptote is just y equals a over b. If the degree of the numerator is less than the degree of the denominator, the x-axis, or the line y equals 0, is the horizontal asymptote. And then finally, when the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So we'll look at three examples showing these three different cases for the existence of the horizontal asymptote. Here in example A, we want to do a couple of things. We want to determine the vertical and horizontal asymptotes of the given functions. All right, so I've factored my denominator because I want to find the places that cause the denominator to be equal to 0. If I simplify this, we get, okay, all right, we get 3x plus 1. It's going to prevent us from saying that there's an asymptote at x equals 0. Because now the x from the denominator is going away. Does that make sense? Okay. So now that it's in its simplified version, we can set those things that still remain in our denominator equal to 0. And so we get 6x equals negative 1, or x equals minus 1 6. Going to be our vertical asymptote is at x equals negative 1 6. To get the horizontal asymptotes, we pay attention to the degrees of the numerator and denominator. Okay, in the original problem, the degree of the numerator is what? 2. The degree of the denominator is 2. So they have the same degree. And the rule said when we have the same degree, we just look at the leading coefficient, and that gives us our horizontal asymptote. So the horizontal asymptote is going to be y equals 3 over 6, or y equals 1/2. Okay. Questions about that? All right, let's see if we can take a quick look at this one to put together the information that we found with what the graph should look like. Three x squared over 6x squared plus x. Okay. All right, so here we have a bit of a picture. Right in here, it looks like we would have an asymptote. Okay, and so that would be at about x equals, what do we find? Negative 1/6. Okay, which is real close. So in here somewhere we've got an asymptote. Also, we can see right in here we've got a horizontal asymptote. You see how the function is tapering off horizontally? Okay, so that value is, we can clearly see that one's 1/2. So we were able to find that information without having to graph the function. We know where the asymptotes are. Okay, very good. All right, let's look at B. Same thing. First, we want to find any vertical asymptote. So we're going to our function f of x equals 2x. On the bottom, we can do what? Factor out x squared times 3x minus 1. Okay, I'm able to cancel out one of the x's. Okay, so we've got 2 over x times 3x minus 1. Okay, so to get my vertical asymptotes, I would say x equals 0, because this time I do still have an x in my denominator. Okay, over here before it was canceled out, but we still have one here. And then 3x minus 1 equals 0. So 3x equals 1, or x equals 1/3. Okay, so our vertical asymptotes are x equals 0 and x equals 1/3. Ready? Okay, for the horizontal asymptotes, when we look at the function, compare the degree of the numerator to that of the denominator, what do we say? Okay. No. There is one. In fact, it's what? Y equals 0. Very good. Y equals 0. Since the degree of the numerator is smaller than that of the denominator, we say the horizontal asymptote is at y equals 0.
And you always have to check that in the original equation?
Yes. Check that in the original equation. Okay? All right, why don't you try C on your own?
Why is that 0 again?
The rule, the second rule, if these were on the page together, you'd see that each of these examples goes with the rule that we had earlier. Oh, where's the thing? The rule says when the degree of the numerator is less than the degree of the denominator, the x-axis, or the line y equals 0, is the horizontal asymptote. So when we looked at it, the degree of the numerator is 1, and the degree of the denominator is 3. So it fits that scenario. Degree of numerator is less than the degree of the denominator. So the horizontal asymptote is y equals 0. Okay.
Why didn't you factor out a 2 or
I could have factored a 2, but that wouldn't have changed my numerator denominator thing. Um, there is no horizontal asymptote in this one because the degree of the numerator is larger. You could do either one first. It doesn't really matter. It might be more efficient to deal with the horizontal asymptote first, since you look at the original equation and you don't change it. Okay, but either one, it doesn't matter. Okay. Other questions about this? Okay, very good. All right. There's one other type of asymptote that I don't think we talk about so much in Math 110, and that is a slant, that should say slant, not slate, asymptote. A linear asymptote that is neither vertical nor horizontal is called a slant asymptote or an oblique asymptote. For any rational function of the form f of x equals p of x over q of x, a slant asymptote occurs when the degree of p of x is exactly one more than the degree of q of x. Okay? Let's see. Let's go back. Yes, it is. Okay? So let's look, see. I didn't put here in the notes, find that slant asymptote, but we do need to know that. So basically what we're going to have to do to get the slant asymptote is something I'm sure you're going to love, and that is long division. Yes, long division. So 6x cubed plus 4x, 3x squared minus 6. Actually. 3x, what was it, squared? Plus x? Minus x. Okay. Okay, so we're going to actually do long division. If you remember how to do that, we got 3x squared minus x. And we're going to divide that into, remember when we do this, save the space. So we got 6x cubed, and then 0x squared, and then 4x, and then we could put a 0 there for the constant. Okay? All right, and we start by looking at the leading coefficient of this thing and asking how many times does it go into 6x cubed? And I think I heard 2x, okay? And then we multiply. 2x times 3x squared gives me 6x cubed. 2x times minus x gives me minus 2x squared. Okay, and now we subtract. Very good. 2x squared, right? Plus 4x. Okay. Okay, we subtracted, so 6x cubed minus 6x cubed is 0. 0 minus negative 2x squared gives me positive 2x squared. And then we just bring down the 4x. Okay? Is that right? Okay. Then we ask, how many times does 3x squared go into 2x squared plus 4x? Does it? No, it doesn't. So this thing might be our remainder. So our answer looks something like this. If we can't reduce it. Can we? Our answer looks like 2x plus 2x squared plus 4x over 3x squared minus x. Okay? All right. If this thing is smaller, which we think it is, we can reduce it some because we can factor out an x, right? Okay. If this thing is smaller, then what's going to happen is as x gets larger and larger and larger, the larger a denominator is, what happens to this piece? It gets smaller. Yes?
Why did you not factor out a numerator of 2x?
I could have, but I guess I didn't because I saw that there was no 2x in the denominator. That's why. So I was looking for things that I could cancel. Okay? But overall, what we see is that this piece, the larger x gets, it's going to go towards 0. Okay? Which means here is our slant asymptote. This is the piece that remains. So in general, the remainder, once we divide this thing, all of that goes towards 0. The piece that we get out, that is going to be our slant asymptote. So y equals 2x. Okay, let's take a look at that to see what it looks like on the graph. Okay. Divided by, remind me one more time, 3x squared. Okay. Okay. All right. So here is a picture of the graph. See what's happening right here? Right in here? Okay, that's that slant asymptote. That's why this thing is is hugging or bending this way. That asymptote, which would be about y equals 2x, is causing the function to bend in there. Okay. So when we divide, we'll do it, I'm sure, again, but when we divide our, whatever that thing is called, that we get out of dividing, is the slant asymptote. The remainder is going to go towards 0, and what we have left, the main part of it, is going to be our slant asymptote. Okay?
I don't mean what do you mean when you say it goes right down?
Remember, we talked about an asymptote is what happens when x gets larger and larger and larger and larger, right? So for the denominator here, as x gets larger, this whole thing is going to go towards 0. For instance, let's say if we have 2x plus 4, let's put 10 in for right now. Okay, then we get what? 24 over 29. Is that right? Okay. If we put in 100, then we're going to get 204 over 299. Is that right? And if we put in 1,000, so this number you can see is getting closer and closer and closer to 0. I mean, we could keep doing it and you would see. So eventually this piece washes out, and this is the thing that's really guiding the function. Okay. All right, other questions? Okay, very good. Slant. Mm-hmm. Because the graph is slanted there. Right. Yeah. I said correct it for. We have the same strategy for graphing that we did before. That is, we are going to find the intercepts. Now we're adding to that to find any vertical, horizontal, or slant asymptotes. We'll look at our derivatives to determine where the function is increasing and decreasing, and also consider what the domain of f is. Okay, we'll look for any critical values and determine any relative max or min, or where the function is increasing and decreasing. Talk about inflection points, concavity, then we're going to sketch the graph. Okay, so let's see if we can do that. And I'm going to pull one from the book. All right, let's start with graphing start with the basic one. F of x equals negative 2 over x plus 5. Okay, f of x equals negative 2 over x plus 5. All right. One of the first things is where the function is or is not defined, and any asymptotes that I'm going to have. Okay. Will I have any horizontal asymptotes? Yes. Okay. Where's the horizontal asymptote going to be? At y equals 0. Very good. Because the degree of our numerator is less than the degree of the denominator. Okay? So put it 0 asymptote. Okay, x equals negative 5. If we set the denominator equal to 0, it's already simplified. So when we set our denominator equal to 0, we get x equals negative 5. So if we want to sketch that information in, okay, so I've got a horizontal asymptote at y equals 0. Okay, so that's my x-axis. I'll just put a little dotted line here in red. And then we're going to have a vertical asymptote at x equals negative 5. So that's over here. All right, so those are some asymptotes we expect will guide our graph. All right. The next thing then is to go ahead and try to figure out where this function is increasing and decreasing. So I'm going to find that out. Plug it into what? We got to find the first derivative. That's where the function is increasing and decreasing. So f of x, of course, is equal to negative 2 times x plus 5 to the negative 1. So f prime of x is going to be what? 2 times x plus 5 to the negative 2. Okay. 2 over x plus 5 squared. Okay.
So in that case, it was just easy as
This was just a constant, so the constant just kind of went along. Okay. All right. But from this, how do we find our critical values? Where what happens? X, or where the function's equal to 0, or where what? It's undefined, right? Okay. Well, this is going to be equal to 0 because the numerator can't be 0. Okay, but it can be undefined. We get x plus 5 equals 0. We already know that. It's at x equals negative 5. So x equals negative 5 is now a critical value. Okay, which makes sense because since we've got an asymptote there, that kind of separates the graph altogether. That's the potential place where it could change from increasing to decreasing. Does that make sense? So we need to check and see what's going on. Okay? So let's set up our intervals. We're going to look from minus infinity to minus 5, and then minus 5 to infinity. Okay, we'll pick a test point, and then another one over here would be 0. Okay, and we just want to know, is the function increasing or decreasing in these intervals? Okay, if we put negative 6 in, we get what? If we get negative right here, but then we square it, so the whole thing is positive. Okay, if we put 0 in, we get what? Positive. Okay, very good. So the function is always increasing, whatever is going on. Okay, we don't have any parts where it's decreasing. Right here? Okay, that's our exponent. So we rewrote it as x plus 5 squared in the denominator. Well, it's easier for us to evaluate it this way.
okay, but if we have to change,
Right. I mean, because if you put, let's say we put the 6 here, we get, or was it negative 6? We get negative 1 to the negative 2. Well, what's negative 1 to the negative 2? Well, see, but it's an exponent, so we're not subtracting, multiplying. So that's why I wrote it this way. Okay. All right. Okay, so we know where it's increasing and decreasing. Now look at the second derivative to figure out something about concavity. Okay, so f double prime of x. I'm looking at, this is a good form for me to take the derivative from. So I'm going to get what? Okay, very good. To the negative 3. Okay. And if I got to plug in, I'd rather plug into x plus 5 cubed. Okay. All right, I think we can already tell that the important point is negative 5. But this time we need to know, is it concave up or concave down? So we intervals, but I'm looking at the second derivative this time. Is that okay? All right. And so when I plug negative 6 in this time, we get what? In our denominator, it's negative, but we've got a negative in the numerator, so the whole thing is positive. Okay. All right. And then when I plug in 0, we're going to get negative. Okay? Alright. As we see, we might think what function is increasing, the slope is increasing, or rather the function's increasing, and it's concave up. What does that look like? Is this what it looks like? Okay. What we might expect. Slope is positive slope, and it's concave up. Okay, so that's what we'd expect from minus infinity to minus 5. Okay, then it says on the other interval, minus 5 to infinity, it's positive slope, but then the function is concave down. So what does that look like? Maybe something like that. Slope is positive here, but the function's concave down. Okay, so the only thing I think we need to complete this graph is just a couple of actual points, and then we'll add these shapes to it, and then we'll be done. Okay? So, and I'm picking these pretty random. What is f of 1? And I need points on the asymptote. So I'm going to, and maybe also, not f of 1, f of negative 1. And also f of negative 3. And then over here we might look at f of negative 6 and f of negative 8. And then let me know what we get, and then we should be done. Well, we already know what these are, but in this case, you know, when we worked on this on Monday, when we found different points, we found the y values that went with them. Well, the only critical value we don't have any one point that we know is on the graph. We just that's right. Okay, so if we plug in negative 1 to the original function, we get what? Negative 2 over, is it negative 0.5 or 0.5? Okay, negative 0.5. All right, so minus 0.5. All right, and then what about for negative 3? Okay, negative 1. All right, and then for, got a 2. And then for minus 8, okay, 0.6, repeat it. Okay, very good. All right, so I'm going to plot these few points. Minus 1, negative 1/2. So that's about right here. And then minus 3, minus 1. Okay. And when we put that with what we said should be happening from minus 5 to infinity, can you see what the graph is supposed to do? Okay. I mean, we already said this is the basic shape that should be happening in this interval, right? Okay. Because the slope is positive and the function is concave down. So now I've got 2 points. I know they're not going to look like a straight line. They're going to look something like this. This one is slightly below this one. So, and here's an asymptote. So the function is going to do something like this. Okay. All right, if we look on the other side, we've got f of negative 6. And you all said it was 2. And then f of negative 8 is basically, so our piece should look like that, first one. And so we'll have our asymptotes. So the function does this. These points were arbitrary. I chose them. You could have chosen something else. Okay. Like I said last time when we did this, we got a lot of different x values for the critical points and a different x value in when we did the thing for concavity. But this time, every time we came up with -5, which was undefined. Any we knew kind of what the shape of the graph was. We didn't have any points to anchor it for us here. Okay. All right. Other questions?
You said that sometimes it can cross the horizontal axis, right?
Mm-hmm.
Or not axis, but
Asymptote.
yeah.
Mm-hmm.
How do we know if it crosses?
Just by again kind of picking a few points. That's all. One thing you do know, if the function crosses the horizontal asymptote, let's say this is my horizontal asymptote. Well, if I go across it, eventually I've got to come back. So it's going to work itself out. But the horizontal asymptote, we might. Okay? All right, very good. Okay, so y'all ready to try that on your own? Sure? Okay. Yes, let's do it. All right, we're going for the gusto. Okay, see what you can find out about this function, and hopefully you'll end up in a graph with a graph. Well, I'll give you some guidance in just a minute. Okay, how many people got this far? Okay, good. Keep going. Remember the vertical asymptotes, we said we had to do it from the simplified version of the function. So the -3, x minus 3's would cancel each other out. We'd only have an asymptote at x equals -5. Well, yeah, if we actually went on and simplified it, then it would be 1 over x plus 5, except at x equals 3. Okay, that's basically what we would say, but don't do anything else from here except determine the vertical asymptotes. Okay, so I'm going to take the derivative from this. Oh boy, we picked a big one. Okay. This is factor, and we already factored this. Okay. People got these critical values. Okay, let's back up. How many people got this derivative? Okay. All right, keep working. I'll pause. Okay, for this we can get or find out where the function is increasing or decreasing. Set up my intervals from minus infinity to -5, -5 to 3, and then 3 to infinity. And should be obvious, but when we do from the smallest to the largest. Okay, so -5 had to come before 3. All right, I'm going to pick a test point. And also, we're going to look at this to see what's happening at f of x, which is right here. Okay, or it's negative x minus 3 squared over okay, I know that the squared is always going to be what? Positive. So I can almost not even worry about that part. So let's look at -6. If I put that up here, that's going well, everything in the numerator is going to be what? We got the same situation. If we didn't have that negative, we'd say everything was going to be positive. But we got the negative out front, so it seems like the thing is decreasing in every one of the intervals. But check it just to be sure. Okay. Is that what you see? Okay, very good. All right, so it looks like it's negative. We have negative slope from minus infinity to -5, and also from -5 to 3, and then 3 to infinity. Okay. We can go on and find our y values to go with these. So f of 3, if we plug that into the original function, what do we get? And also f of -5. Oh, that's right, because that was one of our, we simplified that, we canceled it out, so it's not defined there. Okay, if we plug in -5,
So we plug it into the simplified version, right?
it should work for either one.
Still be under 5.
Yeah, both of those are where we're going to have our asymptotes, right? Okay, so let's draw what we do know so far. I have a horizontal asymptote at y equals 0. And then we're going to have a vertical asymptote at x equals -5 again. All right, so we got that again. Okay, now let's look at concavity. All right, questions? No. Okay. You're actually about to run out. Well, let me tell you what would happen here. We would go on, simplify and factor it, but look at the concavity, find out if there are any intervals, and test from there. Okay? I'm going to ask you to try to do this and bring it back next time. Not for a grade, but please try anyway. Okay? What's that? Yes. Okay, I wanted to make sure we do that. And you have the summary sheet. I'm not taking that up on Tuesday when we get back, but probably shortly thereafter. So please take a look at that and start trying to file these things away. Don't forget everything we've talked about so far. Yes. For which part? I never did plug it in. Did you, William, did you get a value for f of -5?
Well, if you plug it in,
Okay.
because the numerator is x plus 5, x minus
Have a great spring break. Hey, what's your name? I got it here. I'm certain of it. Sure. All right. Hey. Yeah, you were like very, very, very late.